Also, good afternoon, everyone. So we are Facebook. We are the two of us are from the Android emerging markets team in Facebook. I'm Alex Surov, the manager of the emerging market team, and here is.
My name is Alex Petrescu, and I'm a software engineer on the emerging markets team, and I focus on newsfeed.
And today we're going to talk about what we do to make Android apps work better on less powerful devices and less powerful networks. So first of all, why we care about emerging markets. So we have almost 450 million users using the app on a daily basis. And these users are everywhere, and we want to connect users all over the world. As a matter of fact, our Android users in particular are located all over the world. 9 out of 10 of our users are located outside of the United States. And most of the new users who come online are also coming online in places which are emerging markets. We have a lot of people who, for the first time, actually getting internet connections. And of course, Facebook wants to connect everybody, and there is an ongoing effort to do that. Our job is to make sure these users work very well with Facebook for Android app where they are. And where they are typically, with no offense for iOS users, are Android devices, usually cheap Android devices, and network which are not very powerful. So we're going to talk about devices first. Does anybody here care to guess how many different Android devices are out there in the market? Just a number. 500, 1,000, 10,000. The right answer is 10,000. You got that. So there are about 10,000 devices, and actually the number keeps increasing. So that is about 6 months ago, it was about 10,000. I'm not sure what it is right now. And of course, the challenge is how do we actually test and how do we reason about 10,000 devices? They're all very different. Well, the way we reason about them is that we come up with this approach called device year class. So what's device year class? Quite simply, it's no matter when the device was produced, it's the year at which this device with those characteristics would have been the flagship device on the market. So here's how it works. Moto E here is the recent device, pretty popular device from Motorola, of course. Came out in 2014, but it has those characteristics. It has 2 CPU cores, 1.2 gigahertz clock speed, and 1 gigabyte of RAM. And let's compare it with Galaxy S2, which is a very popular device from 2011. Has very similar characteristics as far as these 3 characteristics go. And in 2011, that was the flagship device. So as a result, we're going to say, hey, both of those devices are year class 2011 devices. And again, there are many different characteristics we could have looked at. We looked at all of them. And we thought that these 3 characteristics are the ones that makes the most difference in terms of the performance of the app and how users are able to interface with the app. So these are the actual settings that we look at for these 3 parameters. And here's how we determine whether the device is in one year class or another. On some devices, you are not going to get the exact match. We go for 2 out of 3. If 2 out of 3 actually match the year class, we call those devices from that year class. And that's been a really useful metric for us. It's been useful for us because all of a sudden we can classify this whole world of 10,000 devices into smaller groups, and we can reason about them more easily. So once we actually got this data, we started seeing some interesting trends, and I'll let Alex talk about that.
So we developed the concept of year class a couple years ago. It's mostly just a simple library that we've even open sourced for other developers to be able to introduce this into their apps. And once we looked at the data, we gathered a few months of data. Somewhere around last year, we saw that about a third of all devices will we consider 2010 devices. These are mostly gingerbread devices. You only have 1 core, less than a gigahertz clock, and then usually also other slow characteristics like small cache size and things like that. Another third are 2011 devices, and these are better devices. They have 2 cores, but still not a lot of clock speed, not a lot of RAM. But it seemed that was the majority of users. So we call 2010 and 2011 typical Android devices because they were the majority of the market. And then the ones that we have in our pockets, those are the modern phones, the high-end phones, the 2012. You have more than a couple cores, more than a gig of RAM, things like that. Now, good news is that this year, 2010 has shrunk. So there's a lot less gingerbread devices. There's a lot less single core devices. However, the 2011 class is now the most popular one and continues to grow. Most of the devices sold in emerging markets, where they're selling millions and millions, they're mostly on the 2011 side. So still only 2 cores, which is a challenge. It's a little bit better for the United States. Very few or fewer gingerbread users and single core devices, but still more than a third of users are on 2011 devices. So if you're building an app, you still need to care, and you care about any sort of adoption outside of major markets. You should care about these type of devices. So as engineers, instead of, oh shoot, sorry, I'm bad at this. 1 second. How do I go back? Okay, bam, got it. All right, so as engineers, instead of worrying about 10,000 different devices, now you really only need to worry about 8. And honestly, you only need to worry about 2 or 3. You need to have a 2011 device, you need to have a 2010 device like a Pocket Neo, and then you need to have the device that's in your pocket, which is usually 4 cores or more and a decent speed.
So now that we talked about the diversity of devices, I mean, the next sort of place where there's a lot of diversity in terms of usage is diversity of network conditions. In some ways, it's even more complicated, that diversity of devices. This is kind of the basic graph here that shows you a very basic breakdown on network conditions, and this is just by Wi-Fi and cellular, worldwide. Most of the connections, of course, this is from Facebook data and sessions of Facebook app. Most of the connections out there on Wi-Fi, quite a few cellular, and then about 2% worldwide actually connect where there is no connection whatsoever. I mean, there might be different reasons for that. Users might have turned off the mobile data, or they're in an area where there is no mobile data, or they in the area which is very congested and they can't get to the tower. All of these are reasons for not having any connections at all. So that's simple enough. But when you break it down by countries, you'll see that there's a wide variety of different conditions. Even if you look just at those 3, Wi-Fi, cellular, and no connection whatsoever, these profiles vary a lot. But it actually is even more complicated than that. As I think probably everybody notices that one Wi-Fi is not like another Wi-Fi, and one cellular connection is not like another cellular connection. And so we took the page out of device year class work, and we thought, hey, could we actually do something similar for network connections? Could we actually break it down into easy to understand classifications that we can then use to reason about them and to make improvements for different network connections. And the idea we came up with is network connection class. And again, this is something we open source and others can use as well. But in general, this is fairly straightforward. We are doing a passive measurement of the bandwidth. Like as the app sends the packets and receives them, we keep track of how long it takes, and we measure bandwidth. We throw out small packets because the overhead is actually, starts dominating, and we only look for something which is more than a certain size. And then we get these data points. We get these data points all over the place. The mobile connections are, sort of notoriously, unreliable. And at any given time, you can have a really good connection and a really bad connection, especially if you're moving around. So we average. So we looked at different methods of averaging, and we landed with a geometric averaging. So essentially, we break the space of all the bandwidth into 2 categories. They're all about 4x from each other. Moderate and poor connections are the lowest ones, and then good and excellent. And then, we label them. Again, to label them and understand those boundaries, we look at the data again. We wanted to find the boundaries which are actually meaningful. So as the user moves from one connection class to another, it results in a meaningful change to performance or meaningful change in how the user can actually interact with the apps. So this is the one we came up with. For the open source library, we just label them as poor, moderate, good, and excellent, because in the future we might actually change what the boundaries are. But we found that these 4 are just great groups for engineers to think about and target their app towards. Alex?
So, like Alex mentioned, what we found is technology does not imply speed. And this is pretty apparent to anyone that's actually traveled and tried to use hotel Wi-Fi or try to go into an internet cafe or something like that. Just because you're on Wi-Fi does not mean that you're on a good, fast connection. So when you're thinking about gating very expensive features like, I don't know, autoplay videos or HD videos or things like that, you can't just use that you're on Wi-Fi or not on Wi-Fi, because that doesn't really tell you anything. Again, it doesn't, if you're on LTE connection or a 3G connection, you might have 1 bar or something. Like you're still not getting a good amount of speed. So for example, in India and in the United States, the same download can take 4 times longer or be 4 times faster in the United States on average than in India for the same connection type. So this is what Android gives you. Android tells you you're on Wi-Fi, you're on mobile, you're on Edge, you're on LTE, but it doesn't really tell you what the quality is or how fast you're getting packets to and from your server. So as developers, we need to build one app, usually, that has to work on both 6 megs a second and essentially 56K modem speeds. So it's quite a challenge for developers, and connection classes is something we've developed to help us tackle these types of issues.
And this is a talk about tails and some things that we find out which might not be obvious. And this is one of those things. In general, if you were to have a conditional in your app and say, hey, if I think about Japan, do I think about bad connections or do I think about good connections? I think just everybody would agree that you're thinking about good connections, really good connections for most users in Japan. But when we put this data and started looking at this data, we found this. So at the end of every month, about 10% of users in Japan switch from excellent connections to not so great connections, poor and moderate connections. So we're sort of wondering why. And the title kind of gives it away as to why this happens, the title of the slide. What we think is happening is that basically users are either on prepaid plans or they're basically throttled by their carrier when they use too much data. And so, again, if you are just looking at the country or the type of the connection, Wi-Fi or cellular, you're probably missing out on some group of the population which actually doesn't quite fit the profile.
So you guys have seen this slide a few slides ago, and we talked about the different breakdowns. And what I'd like to point out is now the intermittency issue, is that there's a certain time, no matter what country you're in, no matter what network you're on, where you turn on your app and for some reason you don't have a network right now. This is obviously a much bigger problem in places like India and Nigeria, where something like 20% of all app startups do not have any network at all. But still, even in the United States, we've all been on the subway, on the bus, or something like that, where there's no connection right now. And even though you have a network connection, or Android will tell you you have a network connection, what we found is packets will go out, and then they'll just essentially just go into a black hole somewhere, and then never come back. Nothing comes back. So about what we found is like 20% of all network requests fail, and this is while the app is in the foreground, so we know that the user is trying to use the app. While the app is in the background, it could be 50, 60% if you're trying to make a network request while it's in the background.
So in addition to that, I mean, we believe that improvements, especially on the networking side, are going to take some time. So 2G is being phased out in the US, which is great news, but it's going to be around in the developing, in the emerging market places for a while, at least for a few years. But that's not even the whole problem. The bigger problem is the congestion, because if you go to the emerging marketplace and you try the 3G over there, what will you often find that 3G is not like our 3G here, and the reason is it's really congested and it's not reliable. Congestion comes from a lot of people using the networks, and more and more people are getting online. More and more people are using internet for the first time, and there's fantastic news. Unfortunately, the infrastructure is not catching up with that. So we expect that the congestion issues are going to continue, and the networks are not going to get any more reliable anytime soon. And here's our tale of the connectivity in the Facebook Hyderabad office. So as an emerging market teams, we make trip to emerging market countries pretty regularly. And this year, we really focused on India because we wanted to understand and solve a lot of problems in that market. So we went there twice so far. We went there in January and we went there in July. And when we went there in January, we were disappointed. The connection was too good. You got 3G speeds. The office happens to be in the high-tech part of the town, and they got a lot of cell towers over there, a lot of high-tech companies. So generally, connection was excellent. And I was like, oh, that's too bad. We can't really get a representative sample right there. So we had to fan out of the office and go to like more remote areas and stay in the cafes and coffee shops and just basically see what the connectivity is like. Try to analyze the pattern. Try to analyze what apps works and what don't. So when we came in July, things reversed. All of a sudden, in the office, the conditions were not that great. Or actually, for us, they were great. We got this juicy, intermittency and bad latencies and everything. And so we asked Airtel, which is one of the biggest cell providers over there, what's going on? And they said, well, is there any more construction in the area that happened between January and July? And sure enough, there are 2 new office buildings right next door. I said, well, that's probably between 2,000 and 6,000 people there. So that's what happens. All of a sudden, your network is congested. And we're like, well, what are you guys going to do about this? They said, well, we'll put a new cell tower in the area, but it takes about 6 to 9 months to put a new cell tower in the area. And so in the meantime, that's what you're going to get. So that was actually pretty eye-opening. Like, we tend to think about progress as linear. Things are just improving. And, in reality, it goes kind of like that, right? Sometimes things have to get worse than, before they get better. And Hyderabad is particularly interesting in that, because if you look at this chart over there about population growth in Hyderabad, the city has been growing really fast. So not only are a lot of people coming online for the first time, adding to this congestion, people moving around. And when that happens, more and more people come to one place, they overwhelm the infrastructure.
Yeah, a point about that one. So the last data point is 2011. They've added another 3 million people in the last 4 years. So this year or last year, they had 9 million people. So they added as many people in the last 3 years or 4 years as they added to the previous 10 years before that. So
actually, another interesting anecdote about this is that if you go to a rural area in India, as long as you stay to a major highway, when you leave a large city, your connection improves. Because along the major highways, connectivity is actually pretty decent, and congestion start getting less and less. So like just outside of the cities, as long as you stick to the major highway, you actually have really good connectivity.
So this is everyday life for most people in emerging markets. However, the more we looked at this, the more we realized this is not really just an emerging markets problem. This is really a subway problem. This is a crowded stadium problem. It's a crowded conference problem. This is a road trip problem. This is an airplane problem. Or if you're in New York City or somewhere around, it's your bad reception in your house. So all of these, it's essentially issues boil down to, like, when you're building mobile apps, the network is your enemy. It doesn't really matter how good your phone is. If you're on a bad network, or you happen to be in a situation where you're on a bad network right now, your experience, your user's experience, is going to be pretty terrible.
So when we think about how we address this issue, especially for the network issue, we kind of break it down into different classes. One is the strategies for modern phones. Phone is not a limitation, it's not a constraint, but network is. Like, how do we deal with that? And the other one is the situation where your phone is actually a limitation. So we're going to start talking about the strategies for modern phone first. So phones that actually have storage, phones that have pretty good CPU, and phones that generally look like this computers, the desktop computers of 5 years ago, or even better than that.
So the easiest thing you can do is cache the data that you download. So this is very important when you're trying to, especially for images and a lot of things that take a lot of bytes over the wire. But it's also important for just simple responses, like from your servers for like metadata and things like that. And the reason this is because the user might wake up the app and they might have a network connection right now. Or you might have downloaded data yesterday for a view that they're clicking today. So try to cache as much data as possible. You have the hardware on the device, you have the storage. Your users will generally thank you for it. Also, since you have CPUs and you have cores and threads that are available, try to pre-process your media before uploading. If you're going to use a photo on a site and it's going to be like, I don't know, 1,000 pixels, don't upload a 5 megapixel or 10 megapixel image from the device. Doesn't make any sense to then throw 99% of the bytes away once they get to the server. Pre-process it first on the client and then upload it. Do it in the background, obviously. Tell the user that you're doing stuff so he knows why his phone is hot. But do it on the device. And then make sure, essentially, anytime you're posting, you serialize and you queue these up in the background. So never require network to post data. So if I'm uploading a bunch of photos, allow me to essentially queue those up right now, because that's when I want to do it right now. And then you do it in the background whenever you have a connection. Don't make me essentially wait and look for a spinner. And then use the threads. Especially, like, for example, things like view inflation is very expensive, right? It takes a while, especially on older phones. If you need data for that view, start the network fetch literally as early as possible. Maybe sometimes even on the screen beforehand. So by the time that the view is loaded, they don't have to wait those extra 500 milliseconds a second to do that. So next, use the network cleverly. So we talk about caching. If you have a good cache, one thing you could do is prefetch data. So prefetching comes in different shapes and sizes. It could mean like prefetch for the next 30 seconds of interactions or 3 minutes of interactions, or prefetch for later on today, or if it's like a notification or something like that. So, and then maximize the usage of the network when it's available. If you have a connection right now, you know you need to get a bunch of data for a list view or something like that, try to get it all at once. There's many different reasons for this. Mostly mobile networks are bursty, so once you get a connection, it's great. You have data, stuff are gonna come like over the network very quickly. And also, once it's done, then the radio can go to sleep. So that will use less battery usage, and your users will be happy too. But when you're prefetching, you're doing all this extra stuff, you need to make sure you prioritize cancel requests if the user switches and does something else. If you predicted that they're going to scroll in the list and they decide to click on something, cancel all the requests that you've currently are doing for the list. Chunk responses, especially I talk a lot about lists because I work on newsfeed. Lists are my life. You know, like if you need the data for 10 stories and you're on a fast connection, that's great. Wait till you get those 10 stories because it's only going to take you a few hundred milliseconds. However, if you're on a slow connection, you only need like 2 stories or maybe 5 rows of data in order to show to the user. So just tell the server, give me the first 5, let me process it, and then give me the rest in the background. So you can return those first few responses to the UI very, very quickly. These type of things are great optimizations for just user experience. Keep your requests small, especially when you're sending. Packet size matters. Usually I think it's like 1.5 kilobytes or something like that. Try to fit your request inside of that. So that has the highest likelihood of actually getting to your server quickly. And then this is a hyper optimization, but something that's actually quite important. DNS is quite unreliable for some reason. So even though the user has an active connection, and if you connect via IP, it works fine, often DNS servers will fail, and it's really, really lame. I think like one of the optimizations, I think WhatsApp or something has done, but it's like a great way to essentially just have a fallback. If you can't do a DNS resolution, try to fall back to something else. It might work, and it'll be great for your user.
And you know, prefetching doesn't come without its challenges. I think anybody who actually tried that knows. You know, the challenges are fairly obvious. I mean, it's server CPU, data costs, battery usage, storage, and it can get in the way of your interactions with the user, right? Even if you're trying to prefetch when the user is not doing anything, they can start at any moment, and you know, sometimes canceling those fetches is not cheap. So you know, prefetching is inherently probabilistic, right? Because you're basically guessing that the user is going to use that data, and that's where most of the challenges are going to come from. Because you know, if you guess wrong, you just incur all this cost without any benefit. So to deal with that, you know, we'll talk a little bit about what smart prefetching looks like.
So smart prefetching, because there's lots of challenges. Use the cache data creatively. It's in our app, for example, when you wake up the app initially, we'll show you stories you've already downloaded. We're starting to essentially show you stories that we have in your cache, but you've never seen before. So there's no reason to show you something that we already have and wait for the network. And then this is great because in offline mode, you can still open up our app. You can scroll through your newsfeed. You can like and comment. There won't be any fresh stories. Obviously, you still need a network for that. But there'll be stories relatively recently. And then if you can normalize the data, you might have different endpoints that return different pieces of the story, right? You might have a list view that returns like part of the data and then a detail view that has more data. So essentially, take the data from the list view and put it on top of your detail view while you're loading the rest of the data. So if the user essentially doesn't have to wait for this view to load, he sees something, there's not just a big spinner on screen. And Google has given us Job Scheduler, which has made, and the GCM Network Manager for pre-Lollipop devices, which makes all of this much, much easier and much more efficient. We can optimize for battery usage, make sure these type of prefetches, especially in the background, will happen at the same time with other stuff. They will happen on the types of networks we want. The network will be available. Like I mentioned before, you can start the app in the background, but there's a very high likelihood that the actual your request will fail because they have mobile off or for various reasons. And then you can do things like not prefetch on certain connection types. So we have connection class. And what we found is that on really fast networks, prefetching is useless. Don't do it. It's not worth the cost because you're paying. The amount of time users are waiting is so small that it's not worth you guessing and missing and then using resources in the background and trying to process stuff while the user is doing something. So just don't do it. Doesn't matter which type of device it is. If you're on a fast connection, there's no point in prefetching. You're not going to get a lot of benefit.
Unless it's intermittent and you have to deal with offline.
Sure. There's lots of challenges. And then one of the hardest problems in computer science is like cache invalidation. So making sure when it's keeping your cache fresh. This might mean like periodically doing delta syncs and be like, hey, has anything changed? And the server can just say like yes or no, as opposed to just re-downloading everything all the time.
And then the story we want to tell you here is the story of comment prefetching and how we sort of thought about this. If you use the Facebook app, you know that you generally get the stories, and then to get to the comments, you click on the button. You get the comment counts, but you need to click on the button to go to them. And for a variety of reasons, fetching the comments is a pretty expensive operation and may take some time. So it seemed like an ideal candidate for prefetching. And it does help a lot with performance, but there is a problem. Even users who use the app a lot don't necessarily click on every single comment count and for every single story to see their comments. As a matter of fact, the majority of the stories, users don't click on the comments. They don't look at them. And so the problem is, like, how do you make it efficient? And that's a great scenario for like a more probabilistic approach. So we're going to try to guess whether you can actually gonna read this comment or not. In some cases, it's fairly easy because occasionally we show you a story you've seen before, but it's got more comments and more likes, in which case we're already showing you the story because it's got more comments, so it's a good one to prefetch. In other cases, a little bit trickier. I mean, there are different parameters that we take into consideration, and we actually have a system on the server that does machine learning and tries to figure out like how likely are you to actually look at the comment or not. And then the server sends this probability back to the client, and the client can look at that and say, well, do I want to prefetch or not, depending on what kind of device you're running and what kind of conditions you're under. So that's an example of how probabilistic prefetching works fairly well. That also means that sometimes when you're offline or in a bad connection, occasionally, you click on the comment, it will take some time. But we are generally pretty good about this, and so most of the time when you actually want to look at the comment, it's going to be there for you. So now, strategies for low-end phone. Low-end phones is a completely different situation here, because in the low-end phones, you actually have limitations of the device, and you have to worry about those constraints. And the biggest constraints you have to deal with is space.
So it's a challenge, but if you're targeting low-end phones, one of the biggest hardship users have is that very low disk space. So often upgrading your app or downloading a new app is very challenging for the user. You have to delete one of the other 4 apps that they can have on the phone at the same time. So developing an app that has a lightweight app footprint is paramount for these type of phones. Next, caching is a premium. Again, very low disk storage on the device. So if you're taking up another 100 megs to store images that they may or may not see, that's not going to be a good trade-off for the user. And honestly, for most of these users, the mobile website is their fallback. And it's like, oh, I can't install this app. I really want to use this feature, this service, this website I've heard about. I don't have space to download, or I don't have a good enough connection. So make sure you have a good mobile website. And by good, I mean not a desktop web site that just happens to fit inside of the window. You really need to have one that is specifically focused for these type of users and these type of devices. They're the ones most likely to use this website. So to take a term from web development, you should essentially build progressively enhanced site. Essentially make sure your site has the features necessary without JavaScript, without CSS, because these users might have turned that off because it's slow for them. And then a new thing that has come out in the last year is that you can essentially have many of the benefits of of native applications using push notifications on mobile websites. So we're going to talk about the push notifications a little bit later. So you won't have to deal with these type of phones or networks. These are a little bit older than what we're targeting, but it's still best to send as little data as possible over the wire. We're talking about no metadata at all. If you're not rendering on this screen at this exact point in time, do not send it over the wire. Focus on like essentially formats. JSON is a great format for developers. It's kind of verbose when it comes to devices. So other essentially binary protocols such as like protobufs, or we use flat buffers that allow you essentially to send bytes over the wire and data over the wire without having to pay deserialization costs. And so that goes back to pre-processing data on the server. Don't send metadata. If you're concatenating a bunch of strings, don't do it on the client, do it on the server. Minimize background work and I/O because you only have one core. So it's going to interfere with things that are happening on the UI. It's going to be pretty crappy. And then minimize the number of simultaneous requests. Often on 2G networks and low-end networks, you don't have the available upstream bandwidth to send multiple requests at the same time. So essentially throttle yourself to one request at a time.
Yeah, and you know, some things you just can't do, like on low-end devices, at least we haven't figured out a way to do that. For example, how would you deal with intermittency? Like if you don't have the cache space and you can't really prefetch ahead of time, just pretty hard. But you can do you know, fairly well with in situations where the network is just slow. So the tail here is the mobile web and push notifications. You know, the one thing I want to mention about mobile web is there is a misconception that you know, on Android, you know, mobile web is going down in terms of numbers, and the native applications are going up. And actually, what's true is both are going up. Like, as a lot of users are switching from feature phones, I mean, a lot of them are switching to devices which are just you know, not powerful enough to run some of the functionality we have in the main app, and you know, they opt for using the mobile web instead. And you know, we think with for some devices it's a perfectly great solution to do that. So the usage is growing for both of those, and I think for most other apps that's true as well. And push notifications is just a really exciting topic because up until this year, you know, what push notification in the browser? You know, where did that come from, right? And so this year we actually we originally partnered with the UC Mini and UC browser, which is a very popular browser in China and India, to provide push notifications. And you know, we did that with UC Mini, and then we did it with Opera. And in both cases, we saw just a tremendous response from the users. I mean, they just, you know, they react to push notifications. It's great functionality, and so they visit the app more often. And then we worked with Google. Google is very interested in building it as a platform feature, and they did that. I mean, in Chrome right now, you can have different apps do the same thing that we did and provide push notifications for them. So they have a platform, and apps can actually do that now. And they're seeing similar response for all of them. I mean, it's just been great for users who you know, can't have a native app installed on their device, or prefer to use a mobile web instead. Firefox is the last major mobile browser, and I mean, they announced recently that the support for push notifications is also coming sometime this year. So everybody's moving in that direction. That's pretty great.
I'm gonna stop for questions.
Yeah, I mean, I think we had a lot of materials. We have about 15 minutes more of sort of more material to cover, but we wanted to stop and see if people have any questions before we go on about the material we just presented. If people have general questions, they can also comment afterwards. Anybody? Oh, there's a question there.
So, presenting a lot of content, very big problems to solve. So for, I guess, companies that don't have the resources engineering-wise to do all this, do you have any suggestions for what to pick off, what to start with, instead of going like, oh, our app's terrible, you know, compared to Facebook's?
Right, so
Any typical first steps to go?
right. Right. So the question is, like, a lot of stuff here is pretty high end, you know, like, and maybe utilizing the server power and require a lot of development work. For companies who are just starting to think about the mobile market, the emerging markets, like, what are the you know, the first few things they could do to make things better? Alex, you want to take that?
Sure. I think a lot of the things that we're talking about, things like caching data and optimizing for your app not being online at this very second, are kind of just user experience, and those are just, you just have to be in those have those assumptions when you're building your product. It's really hard to go back afterwards and being like, oh, I'm going to redesign it to work in these things. It's quite challenging. I know, we're doing it. But for it's when you're building for a small company, you can move much faster and you can do a lot. But things like caching data, it's not hard. Like images and things like that, that's no-brainer type stuff. Prefetching and lists and things like that are also not. Understanding your users and their flow, understanding who your users are, so implementing connection class in your class, just purely for your analytics first. That's actually most important, what we found. Just implement it as part of your analytics, try to understand what's going on, and then optimize for scenarios that you see. Like you might see a login flow is like broken and has a huge drop off on year class 2010 devices. So then you can grab a year class 2010 device and then optimize for that, as opposed to trying to do everything up front, which is challenging. So data first, analytics first, and then like find the big problems in your app.
Yeah, and the reason we open source things like year class and network connection classes too, because like a lot of engineers were, in other companies were asking, hey, what can we do? And we thought that would be useful for them as well. But I mean, there are some, basic things, as Alex said, just caching.
And we're going to talk about a few things like right now, some tools and some ideas that we've essentially built into our apps to essentially solve this issue, because it is a very difficult problem.
Any more questions before I move on? All right. So moving on to testing, like we're most of us are here. We have the connections that we have, and they're pretty good. How do we test for bad networks? How do we test for how the apps work? Our apps work on bad networks.
So one of the things we built last year is called Augmented Traffic Control, and it's a tool we've open sourced. It's a server you run on one of the computers in your office, and then it provides essentially you connect to it via Wi-Fi on your phone. So essentially all of the traffic from your app or other apps on your phone could go through augmented traffic control. And then there's presets on there, so you can, for example, see what does my app feel like on 2G in rural India, or when there's a black hole and I'm sending packets out and everything is telling me I have a connection but nothing is coming back. How does my app behave in these type of scenarios? So it's all open source, and you guys can look it up, but essentially it's just a server somewhere with some simple software that will both handle like latency, bandwidth, and also things like intermittency. So like, some requests will be faster than others, they'll be bursty, things like that. It's a more complex modeling. Next, Genymotion is out here, and they're a great tool and a great emulator. So they've built the ability to throttle your network, and they have presets like 3G and 4G and Edge, so you can easily see what it's like. I actually got stuck on one of these modes the other day, and I was like, why is my app so slow? Everything is loading, and I was like, oh, I'm actually on Edge. I was like, this is what people are feeling every single day. It is terrible. I'm sorry. And then there's also the Android emulator, and it provides essentially parameters you can pass in to tell it, I want to be on Edge, I want to be on GPS, I want to be on Wi-Fi, and then like what the actual delay and speed is for those networks.
So, so a lot of these technologies, the sort of Wi-Fi throttling technologies, or some variations of that. And Wi-Fi throttling is used by other companies as well. ETC is not the only solution for that. The tricky thing about Wi-Fi throttling is that you can't really dogfood. You can test, but you can't really dogfood. You can't just take that on a bus and try doing things, right? Or like things you do in a daily life. And dogfooding is very important. Like when we develop our apps, we rely on dogfooding a lot to sort of understand how the features feel and how they work. And so that's a challenge, because with Wi-Fi throttling and ATC, we don't actually get that. So we have a couple of ideas and to how to solve that. And one of them is VPN throttling. Just building a VPN app which can just throttle you as well, and it can throttle you all the time and all the apps on your phone all the time. And it can work with the current network and then just throttle it. So that's one dogfooding solution. But another one, and just to the question about how do you do simple things, is don't underestimate the power of a sleep statement, right, in your app. If you just if you just have it for the dogfooders or for the engineers, where you just slow down your network calls, all of them, that's actually a great way to model latency. just have it parameterizable so you can change this. But that's one way to do that. And another way, simple way to do things, for example, to demonstrate what intermittency might look like, is just fail in network calls. You're not going to get the entire, richness of how the networks work and how many ways they can fail, but it'll give you a basic idea what happens when a network call starts failing randomly and how the app can handle this. And the story I want to tell here is a story of 2G Tuesdays, which is something we started doing internally. And we basically use those techniques, just a simple sleep statement to get the latency and the, have a randomly return network failures, even if the network is perfectly fine. And then we ping employees every Tuesday if you're on an Android device, and we ask you if you want to come in and participate in the 2G Tuesdays. And when you do, you get those latencies and you get those intermittencies. Again, not the entire richness, but you get enough to actually generate a lot of interesting bugs. So obviously users are encouraged to use and dogfood the app as long as they can, as long as they want to. And that's been a great source of bug reports, things which we otherwise would not have found until the app went into the production. And it's also a great way to build empathy, like Alex was talking about. Nothing like just seeing a view like that, for 5-10 seconds to sort of understand what the problem is and really feel the empathy with the people who have to go through this every day.
So next, my favorite thing, because it's actually the solution to all these problems, is configuration. So we build our apps and we usually optimize for a certain scenario, usually our scenario. I open the app and I click these buttons and it works, and I close it and I'm like, it's done. It works. I guarantee it. Then we ship it and someone clicks and then it breaks. And you're like, why did you click it that way? So yes, we're terrible at this. However, constants are bad. That's what we found, is that, I like the quote, the only thing that is constant is change. So we essentially have allowed most, if not all, of our features of our app to have parameters for everything that could be configured. So things that would normally be a static final const in your class is now a parameter. It's still a const, but it could be overridden on the server. And so what we do is then allows us to optimize all sorts of different interactions and feelings inside of our app for your current device. Like, we showed less images on screen depending on your not only device size, but your year class. There's some devices that have big screens and very little RAM. It is really annoying. Or if these devices don't have a lot of disk space, we reduce the cache. If an animation we think is really cool does not perform well, we can just turn it off on certain devices. It's like, oh, year class 2010, there's no point in making the user sit and watch a stuttering animation. We just turn it off and show the screen. And then we can optimize for the current network, which is some of the most powerful stuff that we've been able to do. So examples being like having fewer or more concurrent connections when you're on Wi-Fi. Make all the requests at the same time. It doesn't matter. If you're on 2G, make one request at a time. If you're on 2G, download an image resolution that will load in an appropriate amount of time. Even though it should be 500 by 400 pixels, if that's going to take you 30 seconds to download, no one's going to wait there 30 seconds for this image to download. Download a lower res version to at least show the user in 5-10 seconds. And then you can, I mentioned chunking before, you can change the chunk sizes, and then when to prefetch. Don't prefetch on fast networks, prefetch more on low networks, etc. So experimentation is good. Once you have all these parameters, step number 2, and it's one of the more, it's harder for smaller companies, but you can start out small. Essentially start running A/B tests with different parameters. Don't assume you know as the developer, I know this is how our users should use. You're not Steve Jobs. You need to make sure your app works for the scenarios that your users are actually using. when you're looking at this data, don't settle for the average. Make sure you use the analytics available to you, year class, connection class, country, to really make sure that you're not hurting a certain segment of the population. It might be on average good, but it might hurt a segment of the population really bad. We found, for example, out-of-memory errors for one feature was really bad on one thing, even though for overall it increased engagement and things like that for other people. And then once you've done that, you're not done. Like, you're never done. Especially if you have an app that has a long life cycle and is living over several years. The people who are using your app will change over time. You know, there'll be early adopters first, and then there'll be like grandmas later. They use the app different ways. They have different patterns. You have to make sure that what was true a year ago is still true now.
And our tail here is the tail of mobile config, which is basically our configuration system for doing these things. The key part of the system is we actually want to push a lot of these parameters from the server so we can quickly adjust them or use the power of the server to do analysis and decide, hey, for this type of users, this is the best value. And so that's precisely what we do. So different users can get different parameters and different values. So the behavior of the app, especially infrastructure side, adjusts to what we think is best for them based on experimentation. That system allows us to experiment on things in any time. So even if we are pretty sure that this is the best configuration parameter, it might not be the best configuration parameter 6 months later. So we can repeat this and do it again. In the meantime, I mean, server will just feed you constants, right? From the client perspective, it's just something comes from the sky, and they just use that, right? How it's actually set is not relevant. And one tricky thing about this, in mobile world, especially on Android, people don't upgrade very quickly. I mean, you still have a lot of old versions out there, and you have to sort of honor that. So if you ever build a system like that, you have to worry about versioning and making sure that you can deal with that. There are many different ways to deal with that, but that's one of the problems you have to solve. And then sort of going beyond A/B testing, I want to talk about Facebook Bandit. It's certainly on the high end of what you can do, but it's pretty exciting for us, so we wanted to mention that. It's built by Facebook Research, so a lot of the stuff is pretty complex. So we just want to talk about sort of the basic things involved in the system. It's an advanced experimentation framework. It's common in the industry. It's called multi-arm Bandit. That happens to be the Facebook version of that, the Facebook Bandit. What it allows you to do is to experiment with a large number of configurations. And it very quickly decides how to narrow down to just the configurations which are likely to produce the best results. It's also very quickly decides how to throw out configurations which are producing results which are worse than the status quo, which is important because you don't want to have experiments out there which actually degrade user experience. So that system helps us to get there quickly. And it allows us to optimize for competing variables. Quite often for these configurations, you're not just thinking about one variable. A great example here is data usage. I mean, you do data usage so your performance improves. And users spend more time working with the app than they do looking at the spinner. But data usage itself is, of course, one of the parameters, and you don't want to drive that value too high. And the story here is the story of how we did the prefetching while scrolling. So as we scroll through the news feed, we prefetch stories ahead of time because we don't want you to hit that moment where you're sort of visibly looking at the spinner while we're trying to get the next set of stories. And originally, when we did this, we just said, well, we'll just A/B test, look at a few values, and we find out that generally, worldwide, 10 is a fantastic number, and it could be the best number, and we'll prefetch 10 stories ahead. When you have 10 stories from the moment where we don't have any more stories, we will go ahead and prefetch. And then when the Bandit came onto the scene, we decided that we're going to run this for the Bandit. And so we can figure out the best configurations for different networks in particular, because we had this hunch that for different networks, we might get something different. And Bandit actually went for 27 different configurations. A configuration is something like that, like a little matrix over here, different number of stories that you prefetch ahead for on different connections. And first, they sort of ran them and look at what data usage would look like from different configurations. But the real interesting thing here is optimization for multiple parameters, because you can reduce data usage by doing fewer than 10, but you want to do that in such a way that users don't end up looking at that spinner, because the entire work is there to make sure that you can actually get to to the stories before user gets to them, and so the engagement continues to be high because they're engaging with the app instead of waiting for the stories to load. And so when you actually map this 27 different cases, you see this pattern, which Pareto frontier is just a fancy word of saying, like, for all the other configurations here, there is a better configuration where you can improve on one axis without sacrificing anything on the other, right? And so the tool helps us to figure this out. And actually, it turns out that there are just 4 different values out of this 27 that are like that, which cannot be improved any further on one or the other axis. 2 of them are extreme. You can obviously run with no data usage, but then you're not going to get much out of this. Or you can just say, you're going to get a lot, but data usage is, is still a concern and you have to worry about. And then you just down to 2 values. And then you can A/B test on these 2 values and figure out what the best value is. And I'll let Alex finish on that because that was one of his projects.
Yes. So we started off with 10. That seemed like a good number. We tested out 27 different configuration. And what we found is that 10 was actually a pretty good number. We did a pretty decent job for certain types of users. And it didn't hurt anyone else. But we could actually optimize when you're on good and excellent networks to prefetch less aggressively. So this actually reduced data usage for these people dramatically because now they didn't essentially download things they didn't need, and also decrease server CPU. We saw 57% of users were on Wi-Fi. So 57% of users used to, or some percentage of that 57%, used to prefetch relatively aggressively when they didn't need to. So we were able to drastically reduce server CPU, which costs money, without actually hurting engagement. No one saw any more spinners. Probably no one noticed. So then we just now have one set of values, but we do it based, instead of 10, we now do it based on connection class. So you can see we actually have a JSON configuration object that looks exactly like that. We say when you're on excellent, use 3. When you're on good, use 5. And these will change, right? You might be on an excellent connection now, and you turn off Wi-Fi, and you go walk out the door, and now you need to do another fetch. Now you get the value 10. So these values can change over the lifetime of the app. And that's it. That was a lot.
That's our presentation. So thanks very much for coming. And